ask you a question, first of all, before I start. And that is that Benny has been trying to convince me to give a different talk. So I am not actually sure which talk I'm going to give. So this is the talk that was advertised, but the other talk is something I actually gave in Rehovot a couple of days ago on cryptography and sort of and machine learning. And my question is to the audience, how many people have seen that talk?
Which one?
The one I gave in Rehovot. Okay. And how many people have seen this talk? Which is the talk that I gave at Simon's a few years ago on historical zero knowledge. Oi, okay.
Can you just give both at double speed?
Machine learning, give the one you want.
Yes. You can choose.
Let's vote.
Okay. If it's the one I want to give, then it's the one I gave a couple of days ago. All right. I know more people saw it, but it's fresher. All right, so for me. And then I guess seeing it again, you can doze off if you like. All right, so the talk is really about sort of this history of cryptography and machine learning, past and present, maybe future. And I guess the first sort of point that I want to make is that a lot of research in cryptography has had quite an impact, both on practice and on theory. And in some sense, a lot of this entire conference, I would say, or at least the premise for this conference, not necessarily what people spoke about, is an evidence for that fact. Because zero-knowledge interactive proofs were really motivated by some question about how to, part of the other talk. This was a course that Manuel Blum taught at Berkeley, and Silvio and I were in the audience. And the course was on algorithmic number theory. In the last couple of lectures, he told us about some recent papers in cryptography. That was RSA, the Diffie-Hellman paper, and I think there was a break by Merkel and Hellman, or there was a system by Merkel and Hellman that was broken by Shamir. So there were about 3-4 papers that were known at that time. And it seemed but Manuel had this intuition that all this stuff that he taught in the course, this algorithmic number theory, is going to be useful to do more cryptography. But at that point, it wasn't really quite clear what is more cryptography, what is it more to do. And he proposed this problem of tossing a coin, where there is sort of two parties, Alice and Bob, and they want to toss a coin over the telephone. And this is a toy problem. I mean, tossing a coin is not really something we do even today or envision doing in the future over the telephone. But there was something very beautiful about this question. And in a sense, the way that you would toss a coin, embedded in it also the question of how do you encrypt a single bit. Because you could encrypt the coin toss, send it to the other side, have the other side, guess what the bit was, and then open up and you could compare. If it's the same, then the coin was heads. If it's different, the coin would be tails. So in any case, the reason I'm saying it now is that then the question was sort of how do you prove that you follow the protocol? So that's sort of an immediate question. How do you prove you follow the protocol without revealing what you've done? And that immediately brings up a question of hiding some information and proving proper behavior. The real truth is that zero knowledge came up from trying to come up with a fix or protocol for how to play mental poker, how to deal cards in a game. And again, we had a whole protocol, but in some sense, the way that protocol worked was that it revealed everything about all your strategies. And it's an interesting question how, obviously, when you play poker, you don't reveal your strategy, and we needed to have a mental a protocol where you can prove the steps were followed without actually showing everything you've done. And that led to interactive proof and so forth. All right, this was all my other talk, okay? My point in this slide is that really basic cryptography research has had a lot of impact. In practice, electronic commerce, cryptocurrencies, even in some sense, the fact that there's such a push I think in quantum computing had something to do with the invention of the factoring algorithm on paper by Peter Shor, which was motivated by trying to break RSA. And delegated computing, which you will hear about from Yael later on. And again, back to theory, sort of how NP got a new definition, and also how to define pseudo-randomness in a way that now we all take it for granted. So work of Andy, work of Manuel and Silvio, which really started for cryptographic purposes. You wanted to generate pseudo-random numbers so you can't predict the next bit. And then it was shown that this test of not predicting the next bit is the same as all statistical tests. And that became sort of the working definition. So all this to say that I believe that the next frontier in some sense for cryptography is cryptography and its interaction with machine learning. And that's not just because everybody's talking about machine learning, but I actually believe it, and I will try to convince you. So the way that this talk is going to be is kind of both history and future. So what is the history of the connection between machine learning and cryptography? So this is really goes back to the 80s. And the bit there, really, the basic understanding then was that hardness for one is bliss for the other. So in other words, if you have a problem where cryptographers rejoice because something is true, then machine learning people should be depressed because it means that there's some task they cannot solve. But today, I think that it's actually, the more successful cryptography, the better for machine learning. So there's been sort of a switch, and I'll explain how that came about. So in any case, first of all, what do I mean by machine learning? I'm obviously not going to define it, but let's just think about it. There's some box. It's a magic box that has a formula in it. And this formula or whatever program is in this magic box can be used to answer incredible things. Like, this may be not so incredible, but whether your email is spam, whether your tumor is malignant, should a student be admitted to college, should a bank loan be approved, should a suspect be released on bail? All of these questions there might be some algorithm that can answer all these questions. And obviously, we would love to figure out how does it work? And all we know, let's say, so the question is, before you can figure out how it works, you need to know what information is available about this hidden box, okay? That is, can you query it on X1, X2, X3 of your choice? Can you see samples of this box, random samples? Maybe something else. Maybe you can look partially into this box. Maybe you can look at all its details and try to figure it out. You could look at it for a while, and then you might be able to try to predict it in the future. In any case, it's one thing, what kind of query you have. And the other thing is, what do you mean by successfully learn? So again, these are the type of things that people have come up with. Either come up with an alternative box, which behaves closely to C. Maybe generate data labeled similar to C, okay? Maybe explain properties of C. Let's say, what is the expectation of, what's the variance, what are other parameters of this box, or the distribution produced by this box. And mostly I'll focus on the first one. So in '84, going back in history, Valiant came with this historical paper, Theory of the Learnable, and he defined it to mean that you're given some examples according to some unknown distribution D, which are labeled by this box. So X's are chosen by the distribution, then there's a label, you fit into the box, you get an answer. And the problem of learning is to come up with another box, or another hypothesis H, that's similar to C. Similar meaning it agrees with high probability. It agrees, the error when it doesn't agree is small, and this happens with high probability. And that's why I called it probably and approximately.
So it could be more complicated. H could be much more complicated.
So in Valiant's original paper, I think he wanted H to be from the same class as C, but as far as I'm concerned, let's think that H is more complicated, but it is efficient. So coming up with H should be an efficient procedure, okay? So that's important. That was part of his requirement. Where's efficient here? So we want this process to be efficient. We don't want to try to ask all possible questions from the box and then write a truth table. Okay, and I think that if you look back at Valiant's original paper, he's actually quite optimistic. He talks specifically about DNF, but he asks a whole bunch of questions, like, can you learn it from random examples? Can you learn it if you know what the distribution is? In the beginning, it's without knowing the distribution. Can you learn it by some polynomial time H? That's apropos your question, not necessarily the same class as C. And what if you could not just get examples from distribution, but also allow membership queries? And then there are a series of papers. The sort of NP hardness was kind of clear from the beginning, I think even in Valiant's paper. Then, over the years, people got better and better, but they assumed more and more in terms of knowing the distribution, access to the box. I think the sort of last word on this is by Jackson in '94, where he says that if it's the uniform distribution over the X's and you are allowed membership queries, then you have a polynomial time procedure. But even though his original paper was optimistic and people worked on this over the years, and we're always getting more and more positive results, also at the same time, it was there was a question immediately that arose, which is, are there some concepts which you can prove are impossible to learn? according to his definition. And maybe, in a sense, cryptography played a role here because he was at Harvard and Rivest was at MIT, and these places are not so far apart, and these people talk to each other. Michael Kearns specifically was a student at Harvard, and then he was a postdoc at MIT. And in fact, there was this first paper by Valent and Kearns which showed that if RSA is secure, so reverse Shamir and Allen public key cryptography is secure, that implies the existence of some concepts, some C's in low complexity classes in C, which cannot be learnable according to his model. And it's very clear because if you look at the concepts are, let's say, the composite number of RSA, the encryption x to the e mod n, and the label might be the least significant bit of x. And we know by work of Benny and Oded and other people that predicting this least significant bit even better than 50-50 plus some non-negligible amount is equivalent to inverting the RSA function. So this is something that's going to be hard to learn. There's no hope, okay, if RSA is hard. And then I think Pitt and Wormuth in their paper said that, actually this means also membership queries are not going to help you for some function because if secure pseudorandom functions exist, then it means that you can ask as many questions as you like, and you will still not going to be able to predict another label for some other concept. And you can interpret actually some more recent cryptography. So there's some work with Aloni Cohen and Vinod where we show, we talk about pseudorandom functions that have sort of more sophisticated abilities. For example, you could ask for the number, you could specify an interval and find out all the positive examples in that interval. So just having, in some sense, you can think of it as a negative results for learning, because it says that even if the learner is allowed these extra type of queries, like specifying ranges and number of positive examples and so forth, there's still concepts you can't learn. So it's not just a question of limiting your query to the box in a very severe way. Then there are these, this is work with Elet, work on constrained pseudorandom functions, where even if you allow a peek into the box, and you're allowed to be able to compute the pseudorandom function on some specified x's, okay, fairly general class of x's, you still can't learn the rest of the value of the pseudorandom function on other x's. So in some sense, every result that sort of strengthens the cryptographic agility implies the agility for an adversary and still that there's some security left. Okay, yeah?
Just to point out, I think that the basic connection was also already pointed out by Valent in his original paper. Like without a theorem, but he says that in general, since we have cryptography, we don't expect to learn any function.
Okay, so but I think it's usually attributed to Valent and Kearns the first time. That the NC stuff, right, good. And it's not just learning in the Valiant sense, but then there was this work by Kearns and Danaron and Ronit and a few other people where they introduced another question where there is actually it's very similar to the kind of question people talk today in machine learning, I think in practice, where you want to generate distributions. But so how does that look like? There's some distribution, it's locked in a box, and you'd like to, it computes some sequence of circuits, families, and a learner can request samples, and the task is to come up with another box, which actually has the similar distribution. Again, you could think of it if you want, these cats, which I don't know why these machine learning people are enamored with. I don't even like cats, but because I'm not a machine learning person. So cats and dogs, and then you have successful college essays. Maybe one can relate more to it. CVs to get you a job, slides for keynote talks. So it's obviously a goal that you would like to succeed, but again, there's some paper by Naor that does a lot more than this. But the gist of it, it says that if there's secure digital signature schemes, secure against chosen message attacks. So that means you can give you yourself can sort of request signatures for messages of your choice, and now you can't forge a signature of any other message. Then, in a sense, it means that there are distributions, and even though you can verify they come out of this box because you can verify that these are valid digital signatures, you cannot imitate these distributions. Okay, so these are all impossibility results for learning, right? You can't learn everything if there's pseudorandom functions, even with membership queries. You can't generate distributions, even if you can verify the distributions are correct. They come from the right distribution. So this is in a direction where cryptography says, look, I can show you that you guys can't do anything, or at least you can't do these esoteric tasks. And then in '93, there is this really returning the favor. There's this paper by Lipton, First, Blum, Kearns, where they say Modern cryptography has had considerable impact on the development of computational machine learning or learning theory. Virtually every intractability result invariance model, which is representation independent, so you don't have to be like C, you could be any polynomial time procedure, has its in its heart a cryptographic construction. In this paper, we give results in the reverse direction by showing how to construct several cryptographic primitives based on certain assumptions on the difficulty of learning. So they say, you know what, here's a problem in learning. Maybe that could be useful for cryptography, not just the other way around. And the problem they're talking about is learning parity with noise. So there's some vector S, which is a binary vector, and let's say of dimension n. And the learning parity with noise is you're given a whole bunch of equations. The S's are known. But the thing is, you're not obviously giving the equations correctly, because otherwise you could do Gaussian elimination, but you are given the right-hand side is flipped with some probability. And the question is, you want to learn S. And now the question is, how hard is this? And this is related to, of course, what's the probability you flipped on the right-hand side. And then the best algorithm for that is by Blum and Adam Kalai and Wasserman, which is this. This is the best we know even today. This is a good problem to improve it. It's since 2003. And another question you can ask about this, which is a cryptographic-like question, is this problem hard in the worst case? Is it hard on the average? And what we know today, these are very recent results. I think this is Brakersky, Lubachevsky, Vaikuntanathan, Wicks, okay. And they show a worst case versus average result for this, but in some sense it's fairly weak because it says if the noise is really, really high, okay? So it's essentially a half minus a little bit. Okay, so it's sort of the hardest average case instance is equivalent to a worst case instance, which is probably the easiest worst case that we don't know how to solve yet, and that's decoding for relative distance log squared n over n. So that's a decoding problem, which is, you know, that's about the barrier where we don't know how to decode. But in any case, they do show some average to worst case reduction. The more important part is that Regev, actually, yesterday we had an argument whether it was in Tel Aviv or in IAS. Everybody's trying to take credit. But in any case, he was a faculty member at Tel Aviv at the time. He said, you know what, why learning parity with noise when the mod 2? Why don't we talk about mod P? And P is prime, say, or in a field, and think about this vector S, not just a binary vector, but a vector in this field. And then on the right-hand side, we don't just flip a bit from 0 to 1 or 1 to 0, but we add some noise, some Gaussian noise between, let's say, if Q is the prime. So we're working in ZQ between Q over 2 and minus Q over 2. And so it's a different noise model, but it's the same problem in a natural way extended over the ZQ. But the miraculous thing is that he shows then this, which is he shows sort of a worst case to average reduction by showing that this is equivalent to approximating the size of the shortest vector in a worst case integer lattice. Okay, and this goes through, you know, okay, so he shows this. It's actually a quantum reduction, so he shows this with respect to quantum algorithms. So if you could solve by a quantum algorithm this shortest vector, then you could solve by a quantum algorithm this, I think that's the statement. Since then, it's become classical, this reduction. But this was very important because at that point, Aitai already showed also some worst case to average for the worst case for integer lattice problem. So all of a sudden, you had a new problem. It looks like solving these equations. And you know that it's as hard as the worst case lattice problem, which has been studied for many years. So it's not just some problem for machine learning that people have come up with. And the most important thing is that this is a problem that's very easy to work with. So it's been sort of revolutionary for cryptography. So we are able now to do things like homomorphic encryption. I'm sure everybody's heard about it. You know, with this breakthrough by Gentry in 2008, it's really, you know, in some sense, working with this problem. And then there's Brakersky, Vaikuntanathan Gentry. Not only that, but you could do leakage resilient cryptography, functional attribute encryption, and much more. So this problem, this is really a fundamental change for cryptography. We've sort of gone to be able to do many things that we couldn't even imagine before because this problem is so pliable and easy to work with. So you can't underestimate the importance of which hard problem you're working with and the structure. Eventually, we want to say that it's true if any one-way function exists. But the history of cryptography is always we start with some concrete problem that had structure, like RSA, like quadratic residues, and now with learning with errors. And still, the best algorithm known is this one. Obviously, this is harder than the mod 2 because 2 is just an example of this general problem. Okay, so it's still the case that if you look at cryptographic construction from learning with errors versus learning parity with noise, you could do a lot more with learning with errors. You could do something with learning parity with noise, like the one-way functions. I think there's now a result about public key encryption. It's through random number generation. But the noise level is much, I mean, you have to assume that the probability of flipping the right-hand side of the equation is very, very high. And so these are, in a sense, we are much more comfortable with LWE, but it would be interesting to get more construction under learning parity with noise, because it would be more efficient, you're working mod 2, and so forth. Okay, so this is really almost like a cryptography talk, but that's okay. You learned something. Then there is sort of the quantum significance of this whole thing, and that is that we don't know how to break learning with errors even with a quantum algorithm. That's one of the big problems out there. I don't know what I would bet on. But today, people know how to factor on paper with quantum algorithms, solve discrete log, solve elliptic log, but we have no clue really of how to solve this problem. And you could say, well, who really cares? Are there any quantum computers out there? So as Andy knows, many governments and then also many companies do believe that this is only a question of time. Of course, it's a question of how much time. Right? I think that's the question. But in any case, it's very prudent for the National Institute of Standards, NSA, to start to plan for post-quantum cryptography. So let's say everything we do on the internet, transactions, blah, blah, blah. You want to make sure that one day, if in fact this is successful, you're not going to just lose the whole infrastructure. And the only candidate, essentially the only candidate, are based on, well, Adi disagreed with me 2 days ago. Whatever. In any case, most of the candidates are based on some version of LWE. Apparently, there's some other candidates. Okay, so that's kind of a downer, right? It means that every time we make progress in cryptography, the machine learning people realize that theory is not in their grasp. In some sense, they can maybe distinguish cats from dogs and all that, but they will never be able to prove anything about it. But I guess now we switch to the second part of the talk, okay? So in some sense, I think that, cryptography, theory and practice have gone really hand in hand. So I was in the first crypto conference in 1981, and there was really a very big divide. There's some people from theory, but most people were from practice, were breaking schemes. And in terms of machine learning, theory and practice, also I think the theory was a very big driver in machine learning, like with boosting, with AdaBoost and so forth, and SVMs. So it had a clear impact on practice. But today, most of the excitement is in deep neural nets, right? And it's certainly in practice, and there is no theory. So that's a big place for machine learning people. So in some sense, they are kind of going further apart rather than getting back together. And I guess the message here is that the practice of ML is too important to leave to practice. So this is a crowd of theoreticians. And because it really is invading, in a good way, I don't necessarily mean invading in a bad way, all walks of life, because we have so much, what? Yeah, that's true. So everything, right? We know all this, that there's all these walks, all these areas where having a lot of data is enabling machine learning to make progress in some sort of an obtuse way. The fact is that it's successful. But then it's starting to be relevant to policing, to bail, to credit rating. I think where is it? There's the Mardi Gras. New Orleans. In New Orleans, apparently, they send police cars to particular neighborhoods according to some computer algorithm. That's already done. I think in New Jersey, the court systems have actually come forth with the fact that they use automated procedures to set bail. So there's this sudden shift of power, that things that were decided by humans, which are fallible as well, But at least there's procedures that we have understood and are able to kind of question, are now decided by algorithms. And algorithms, algorithms have bugs. Algorithms we don't necessarily understand. They don't necessarily explain themselves. So there's this sudden shift of power, which is, we can discuss it over cocktail parties as much as we like. There's also sort of dollars and cents. So it used to be that if you saw companies that had the part of the lion's share of the market. It used to be, let's say in 2001, gas companies or power companies like Exxon, like GE. And these days it's all data. It's all companies that hold data. So there are these quotes about data being the new oil, you know, and data will become a currency. And I think that's the feeling, that the more data you have, even if people don't understand how to translate their data to commodities, the feeling is that then they will be more successful in prediction and they will hold the power. So the question really is, it's kind of a societal question, and this sudden shift of power can really leave us unprotected and unregulated. And I think that that's a fact. And the question is, we can wait till that happens and then kind of go backtrack, or we can sort of do something about it now. And the thesis for the second part of the talk is that essentially 30 plus or 40 years, cryptography has been devoted to privacy and correctness of computation. So correctness of computation is really proofs. So this is a connection with this talk. There's a lot of tools that we have. And I think that there's tools, our ability to model, means that we can play a central role in ensuring that this power of machine learning algorithms is not abused, at least to some extent. So maybe this is what I'm going to call safe machine learning. And in the next few slides, I'll show you a few challenges that I believe that cryptography has a place to play. The kind of cryptographic tools, proofs, encryption, could actually make a difference in this control of the shift of power. Okay, so the first thing is obviously, if we say, this is like a very clear sequence of implications, if the power of machine learning come from data, and data is data held either by individuals or that you gave your data to some custodian like Google, like Facebook, like whoever it is, like your doctor, then protecting that data and not just giving it away will mean that you keep some sort of power. And that means that we need to ensure sort of the privacy of both the data and the model during what we call training, right? Training is when you give examples, you're given examples and then you're trying to come up with that boxy and a classification. So now the boxy has already been created and somebody's going to make a decision about your own data. All right, and most of the work that's done today is actually on one, and I'll describe to you some breakthroughs, fairly recent breakthroughs on this first challenge. The second challenge, which is more related to what we're talking about in this conference, or at least the premise of the conference, is that the models, it's very important that these models will not be tampered with, nor introduce a bias for profit or control. So let's say that there's a data set, okay, that we all agree is the right data set that you want the machine learning algorithm to use in order to create a model. How do you actually make sure that some of this data was not maliciously chosen, you know, and so that to affect the model? So you want to develop some methods to minimize the influence of these maliciously chosen training data. Now, what the goal of the person who's choosing this data might be is just to bias the entire decision process, or maybe they are thinking it's like a sting operation. They're going to give some maliciously chosen data so that later in classification time they may be able to be classified in such a way to ensure much more profit. Okay, so the adversarial goal could be much more sophisticated than one thinks, and then you want to be able to efficiently prove to a client that the model is consistent, let's say, with a data set. That's where proofs come in. But that's very different than delegating computation, because what you're proving is consistency with a data set, and it's not an exact one, but maybe sort of a statistical consistency. And basically, I would say that for these two challenges, we have a lot of tools already that we can use. Okay, we need to develop more, but we have already tools that we can use. What's some other challenges where it's not so clear and there's more theory to be developed? So for example, so everybody knows about adversarial machine learning, or at least most of you know, and that is where this is the model, there's some adversary, and he can ask questions from the model. And their goal is to come up, after asking enough questions, to come up with some example where it will be misclassified. So people always give the example of self-driving cars, that they need to identify stop signs or dangerous situations, and they will misidentify them as something that's not so dangerous and take the wrong action. And people have looked at either letting this adversary look at all the wires here, or which is called white box, or actually ask questions. And does cryptography have anything to say about that? That's an interesting question, right? Because sort of intuitively, I would think it does. And here's some evidence to that. So as cryptographers, we have considerable experience in essentially modeling adversarial behavior. So that's kind of what we do, right? Different tasks, different adversary, and you would like to model it as general as possible and show something that's robust against it. So for example, Alexandre Madrazo at MIT has done a lot of work on this, and he always goes around saying that he's inspired sort of by cryptographic thinking in the following sense. He says what he's done in his works is he takes like a domain-specific attack. So in cryptography, we usually don't do that, but machine learning makes sense since the successes are also domain-specific. Say the cats and the dogs and the pictures. So he says, what are natural transformations you can do to a picture? That will be his attack space. And then he has some papers showing how to achieve robustness against an adversary that's trying to misclassify via robust training. So in other words, in the training time, he gives things which are properly labeled, and then he gives things that were generated by the adversary. And by doing that in the right quantitative way, he can show some results about how this protects against adversarial misclassification. This whole thing is quantitative, right? So it's a question of how many questions you ask that black box in order to attack. Obviously, if you ask all possible questions, you could attack, but you want to show that, I mean, the adversary wants to ask a few questions and get an attack. You want to train in such a way that they will have to ask lots of questions and then attack. Okay, so that's one thing, is sort of to define a class of domain-specific attacks and protect against them. Another thing is, you know, people here, some people follow this literature, is that in cryptography there was a period we were talking about these leakage attacks, where cache attacks, timing attacks, putting a cryptographic algorithm in a microwave, whatever, you know, things of that sort, and then show that this could break a system completely, which is kind of a side channel because it's not the interface that was defined with the cryptographic primitive. And after a while, we said, okay, let's try to generalize all these attacks by saying it's any algorithm that attacks, we don't know how, but at the end it leaves some entropy in the secret key, and then develop encryption schemes which were robust against it. So also here you could imagine that one could take all these different attacks that have against machine learning algorithms, try to come up with a definition which is much more general than some domain-specific definition. But definition that maybe it says that it leaves some entropy in the black box, and now what can you prove? Finally, I would say kind of the holy grail here is how to build machine learning models where misclassification requires learning some cryptographically hard task. So somehow embed in your question the knowledge of the fact that you didn't perturb it. So it's, I don't know if this is possible or not, but obviously this would be something that would be very desirable, to show that it's impossible to misclassify, because that would imply that you're solving also a cryptographic challenge. So some people talk about go to stop signs and putting stickers on them, where the sticker is such that if you could, that it essentially necessitates the ability to sign digital signatures, okay, in order to misclassify. But of course, the objection to that is who's going to go and put stickers on all stop signs? You would like it to be somehow more of a natural process. What?
If you do that, you could also maybe don't need to learn. Maybe you could have like a barcode that says this is a stop sign.
That's true. So if you had that ability, then you could do other things. So this is from Saturday Night Live. There's this character called Debbie Downer that everything was like, you know, everything was terrible. So, you know, it's good for cryptography, it's bad for machine learning. Everything, you know, no matter what you said you got $1 million, it wasn't 100 million, that kind of thing. Okay.
Every silver lining has a cloud.
Exactly, exactly. So we call Debbie Downer. So in some sense, having a hard cryptographic task would be a good we want to think of it as a silver lining. So maybe it's too optimistic. Okay, so this is a lot of writing. Sorry about that, but I'll explain it. So maybe that's too optimistic. So I was just in NeurIPS, so the new name for NIPS in Montreal, and there's a very interesting sequence of paper by Mahmoudi where he says that there's some paper where he actually shows in some sense that this might not be so easy or maybe impossible. Maybe you're on some of these papers. I have no idea, but he was your student. Okay, so in any case, so he says, let's think about something called learning under p-tampering, where there's some random corruption model in the training time. So he actually talks about this. Suppose someone is training in order to misclassify later, okay? That's their goal. They take your training data and they do something to it all the time thinking that they want to misclassify something. And the kind of, what they're doing is corrupting in some sort of random corruption model, okay, during training. And then he shows that any learning algorithm that has sample complexity m, so if you kind of fix it and say that the complexity size of the sample is m, then, and any efficiently computable predicate defining some bad property b, so this could be a misclassification, think about that, for some produced hypothesis that happens with an initial, whatever, there's more details here. He claims that he has a polynomial time tampering attack that tampers with square root of m of the training data. So m was how many? You have to change square root of m of them, and then you will be able to misclassify to come up with another example for which this bad event happens. Okay, so things are misclassified. And it's kind of very interesting, this paper, because the way he does it is actually using results actually by Yael and Sanu Park and myself, and then results by Yael and Ilan Komorowski and Ran about coin tossing. So interestingly, he sort of thinks about this as a way, as the machine learning algorithm as sort of an interaction between two people trying to toss a coin. And the ability to bias the coin is translated to the ability to bias later to misclassify. So again, some very, at least someone who knows the crypto and comes from the crypto, both in terms of how you attack and show that it's impossible, was able to show this result. In some sense, I'm not happy about this because it's, again, Debbie Downer kind of thing, right? He talks about the impossibility of, but if you show a protocol where you can maybe come up with a fair coin, then maybe that could be translated to a positive result.
But his window of tampering is sort of within some error on the distribution?
Is window of
Like
tampering.
How can we tamper? What's that?
Okay, how I don't know. What he's saying is, if I was in control, so where is this data coming from anyway? That's a good question. Who's giving you this data? We'll talk about it a little bit later, but let's say this data is given by crowdsourcing, or maybe you had access to the data, or maybe you, then he says if you could modify square root of m of the samples, which is not that much, right? Or you had control over square root of m, with your mind later that you want to have some bad events happen, then you can do it. What else? So another challenge is, you know, there's all these there's this regulation called GDPR with the Europeans. They're saying you're not allowed to give my data away to someone else, and if it's been discovered that you have, okay, or you're not shepherding my data, or you're not protecting it, then the companies will be subject to high penalties. The thing is that how do you know that they followed the regulations? They claim they did. Maybe if you're Google or Facebook, you're going to do what you claim. Facebook, I don't know, but certainly, let's say maybe if you're a large company, you'll do what you're supposed to. But how do you prove that you have done that? So it would be very interesting to find ways to sort of trace unauthorized use of your data. So this is just also in California, there's a new rule about consumers should have control and insight into the spread of their personal information. But these things are very informal. You know, there are these laws, okay? You assume that somehow you have a way to impose it. How do you do that? So one way you could think about is that you design a method so that you can catch people in the act if they don't follow some, let's say, they didn't do what they claimed they did in terms of trying to ensure privacy of your data. So we want to develop methods to trace training data used for learning a model without introducing new vulnerabilities. Someone would like to trace. So now it's sort of counterintuitive, because if you have ways to trace, then it seems like they've left some signature of you in there. So it would be much more useful if you could maybe come up with a privacy method, okay, where you would show data tracing is possible unless that privacy method, so an if and only if. So if they use the privacy method, let's say differential privacy, then you can't, but if they didn't, if they just sort of make it tight. Differential privacy is not tight, it's a very strong requirement, right? So if you follow it, if you don't follow it, it's not like that can be detected. You would want something that's sort of an if and only if. And in fact, again, in the same NeurIPS, there was a paper by John Ducci and a bunch of people from Google, which is kind of interesting. They said, maybe differential privacy where you cannot even detect if somebody's data was in or out of the training set is too strong. Maybe we want to prevent is reconstruction of private data. And they say if you relax the requirement of differential privacy to reconstruction of private data, then they claim that even if you do differential privacy with a very large privacy budget, so you allow more privacy leaks, implies that you cannot reconstruct. But this is only when the data there's no prior over the data. But this kind of work is starting to be to be talked about, sort of trying to show what's the minimal amount of, let's say, differential privacy or privacy preserving to prevent real breaches that can be recognized. And again, that's similar to what was going on in cryptography, because a lot of people here know about zero knowledge, but there have been relaxations of it. There's something called witness hiding, witness indistinguishability, and maybe that's the way that this differential privacy is going as well. Okay, now so that's what I had here. So protection against reconstruction. Next thing is not only that you want to trace unauthorized use of data, but also unauthorized use of the model. So what does that mean? Maybe somebody stole your model. Okay, you would like to be able to watermark that. So there is actually some very nice work by Benny Pincus and some other people in Bar-Ilan, where they talk about turning your weakness into your strength. And what they do is they say, okay, this is a way to watermark deep neural nets. So they say, well, okay, we know that you could do adversarial machine learning, and that's a bad thing, but we'll turn it into a good thing, because we're going to essentially train the network to accept some planted adversarial examples, okay? And then if somebody steals it, they're not going to be able to tell where we planted those adversarial examples. And I could show later on that somebody stole my model by showing here's an example that obviously should not be accepted, and it is accepted. So it's an interesting paper. Another thing, I guess, is the fact that a lot of people are now talking about the fact that these machine learning algorithms might not be fair. There's this famous Benny, אתה יודע הכל. What's the name of that newspaper where they discovered the unfairness? Publica, right. Where they said that a lot of these machine learning algorithms are unfair. We know they're not accountable, interpretable. And all the definitions now are very they're based on this notion of similarity. So if groups, people are similar to each other, then they should be treated in the same way. But I think that, we have a lot of crypto-style definitions where we use sort of simulation-based definition. For example, like let's say that you want everything you can do with, let's say, people should be the same regardless of the group that they belong to. You could imagine that our type of definitions could be very relevant to defining these notions. What's another thing? Randomness. So again, pseudo-randomness, as I said in the beginning, this work by Andy, by Manuel, by Silvio about how to define pseudo-randomness came from crypto unpredictability. What kind of randomness is necessary for machine learning? Do you need it to be secret? Does it need to be unpredictable? Is it good enough to use linear congruentials? How is it generated? A lot of the breaks in crypto are essentially by having control over pseudorandom numbers. If you know the kind of pseudorandom numbers used for keys, you can break cryptography. What about here? If you had some control on the randomness used for the weights, let's say in a DNN, does that mean that you can affect how it will behave? This is something that's, I think, would be interesting to study. Another thing is and that's actually something I'm going to talk about in a minute, is, if you wanted to make sure that machine learning is done, but data is protected, both in training and in classification, and bias is not introduced and so forth, I think you have to use cryptography. But cryptography is not for free. So there's sort of cheaper and more expensive cryptography. And some of these two fields working together might mean that you might want to change the way you do machine learning to be more cryptographic friendly. So I think that's important, to come up with some specialized cryptographic functionalities which are sort of ML complete, and then show how to do them efficiently. So I think it's a real opportunity for developing new theory. And I'm done with sort of these challenges. There are more, but I'm good at these challenges. Now one has to solve them also. So let me tell you what people are doing in the last, 2-3 years about trying to solve some of these challenges. Essentially, they really are doing things about the first challenge, about how to keep privacy. And I would say there's sort of 3 categories. There is, what do you do? And I'll explain what I mean by this classification, training, and model stealing in terms of what kind of privacy concerns come up and what's being done. So there's lots of work. It's amazing how much work can be generated in 3-4 years. And it's getting sort of better because efficiency is important in this space. Okay, so what kind of cryptography it starts with garbled circuits that really go back to 1985 with Andy's work, and differential privacy with Cynthia et al.'s work, and Irit and Kobe, multi-party computation, both the GMW, BGW, secret sharing, and homomorphic encryption is sort of the new game in town, where you can encrypt data and then compute on it while it's encrypted, and then just give the encrypted result. So these are all different type of algorithms. There's a lot of work, a lot of papers, even companies that dedicate themselves to using one of these technology or another, and all of them seem to be relevant to trying to solve this privacy problem for machine learning. I'll give you a little bit of a hint. I think I have 10 more minutes. But before I give you the hint, it really is kind of a pick and choose approach. It's sort of a Chinese menu, although this doesn't seem like Chinese food. You take what you need and you glue it together, and then you have a system. Okay, so let's look at this classification stage. Okay, so there are two stages, right? Sorry, the classification stage is over here. So we have already a model that has been developed. We have a client. Okay, they are the two parties. And what is the model? The person who has the model might be a hospital. And let's say that the model is sensitive because it has patients' data, because you want to monetize it, whatever. So that's the server doesn't want to reveal the model, and the client doesn't want to reveal her data. So she might have a medical record. So you can think about the model as something that takes an MRI image and says whether you have a tumor. So there are two opposing concerns. So it seems like it's a straightforward two-party computation. Two parties, two privacy concerns. Why don't you just use garbled circuits and be done with it? You could. However, we also have this homomorphic encryption that came up. And the kind of things that people are doing is they're saying, wait a second, should I use two-party computation? Should I use homomorphic encryption where the client encrypts their data, the hospital encrypts their model, and somehow there's a computation of running the model on the client's data, and the result comes. But there's sort of pros and cons to both methods. So secure, two-party, n-party is actually much more efficient computationally. Usually it's much faster to run it, but it's not so good on communication. So the amount of communication that has to go between parties is proportional to the size of the model. So sort of in some sense, every wire in the algorithm, if you think about it as a circuit, requires more communication. And on the other hand, if you talk about homomorphic encryption, the communication is very efficient, because in some sense you sort of send your input and get back an output. That's the communication that goes on. But computationally it's expensive. What again is nice about homomorphic encryption is that it's very linear algebra friendly. So a lot of the machine learning, especially the modern one, the basic operations are matrix inversions, matrix multiplication, vector matrix type of operations, transpose, FFTs, and that's kind of native to the homomorphic encryption that's out there. And also arithmetic computation is native to it, whereas here you really are working more on sort of Boolean circuits. So when you come to decide what to use, you have to sort of think about this. So there's this paper now. So this is some work that I did about doing it for simple classifiers in 2015, linear classifiers. But I think it's much more interesting to look at this modern work, which has to do with neural nets. So in a minute, I'll explain it. So neural nets, we all kind of know probably. You've got inputs, you've got outputs. You have these different layers. These wires essentially are doing weighted sums on your inputs, and that's true in every level. So what's challenging here is these round circles are non-linear operations where you sort of want to decide whether you're kind of above or below, whether you're 0 or 1. So sort of, and usually that's done by using some sort of very highly nonlinear functions, like ReLU, like some trigonometric functions. And the thing is that if we were thinking about encrypting the inputs, okay, and then doing weighted sum of the encryptions, and then evaluating under encryption these functions and keep going, it's just not the kind of encryption basic operations we have are it would be very expensive to implement these functions. It's just we approximate by a very high order polynomial. It's infeasible, even though in principle you could have done it. So why not use two-party computation? Well, because the circuit size is going to be essentially quadratic, because you have to kind of do communication for every wire. So this is a typical, in the sense that this is the application, right, that we now want to address. And there is this There should have been. Sorry. How did that go? Disappeared. Just 1 second. Yeah. Okay. So okay, so how is it done still? So the way it's done is first idea that people have used was to replace this activation function by something that's a low-degree polynomial, like squaring. This is work by Kristen Lauter and the Microsoft team. Essentially, the big idea here is you want to trade accuracy for efficiency. So instead, let's say the neural net really would do better if it used a ReLU or a sigmoid or something. But you're saying, I can't handle it with a cryptographic function. I will change the neural network to use a squaring function that I can handle. So that's one big idea.
How much worse is it?
What?
Is it really worse to use the squaring?
That's a great question. Okay, so they claim on some small data sets that it's not worse. But I think that's a question to the machine learning people, right? To try to start using these functions and to see how accurate their models become. And for that, they have to know that cryptography needs it. It seems to come to surprise to most people that I've talked to in machine learning. Another idea is to essentially realize in a more concrete fashion, when is it that FHE is better than MPC? So if this is the rule of thumb, that when the computation is linear and the circuit size is superlinear, then you should use FHE. Let's say that that's the rule of thumb. So when the computation grows too much, it means also something for the communication. So in fact, there's this work by Vinod and Chirag and Anantha, the dean of engineering school at MIT, where they say, why don't we use both? Why don't we, for a neural net, for example, do the linear layer? So in some sense, you have two parties there. One of them has the data. They encrypt it. They know the key. The other party has the model. You send them the encrypted data. They do the homomorphic evaluation, which is linear, just by summing weights on the encryption. And now there's a two-part. Now when you get to the nonlinear layer, you do a two-party computation, where one side has a key, a decryption key, and the other side has an encrypted value. And it enables them to go to the next level. And to know whether the inputs to the next levels are zeros and ones. And you do this, so you have two-party computation, but it's many times as the number of layers. And other than that, you're doing it sort of on encrypted values. So this idea of using both technologies has been used in this paper, and they claim very good results as compared to unencrypted. With very small overhead, a few, usually we factor 10 more slower. That's amazing, actually, for this space. And in fact, there's a homomorphic encryption library with native support for these neural network layers now. What else I want to say about this? What about training phase? So training phase means that you have lots and lots and lots of encrypted training data, and you have to kind of update the weights of the neural net, say. So this is a huge amount of nonlinearity. It's not just one example that you're trying to classify. So in some sense, it's sort of the size of the data set factor. And the data sets here are insane, yeah? Another issue with training is that usually the training examples are coming from individuals or multiple institutes. So how do you get all this to work together? I mean, do they tell each other all their data? Do they tell it to a centralized server? So in terms of what's done, at this point, I think people do things like linear regression, or, logistic regression, all kinds of regressions. So that is not going through a whole neural net. And again, what they do is they use there's this paper, beautiful paper by this Korean team, Kim Lee Cheon, where they come up with a completely new homomorphic encryption method, not along the pattern of the Gentry, Berkersky, Vicontinathan, but it's an encryption method where the basic operations have error in them. So in some sense, there's a decryption. Usually you want to say, I've done encryption, but I'm getting exactly the same result as an unencrypted model. I'm not giving up anything, but I'm adding privacy. They say, you know what, let's give up a little bit. Now we're going to have, the circuit at the end will compute something which is not accurate once you've introduced encryption. You lose some bits of accuracy in the, in the computation, at the output. But they're saying if you're using all of this for a machine learning model, accuracy anyway is not holy. So it could be that what you're getting is accurate enough, maybe you haven't lost much accuracy, but you've managed to do the homomorphic encryption in a much more efficient way. So it's a very interesting, so it's not just trading efficiency by, changing the machine learning model, but actually saying, let's change the encryption. Let's not guarantee what we always guarantee, and that's good enough for this set of applications. Very interesting paper. Really beautiful, using sort of, why don't you pick up the call? Okay, good. I sympathize, but still, now I'm the speaker, not the, the audience. It's very interesting also because the kind of operations they do, they use trigonometry in order to do things like bootstrapping. I mean, they use mathematics from a domain that you wouldn't think about in order to do cryptographic operations. I think it's fascinating. Okay, let's skip this, theory to practice. Am I out of time already? Not yet. So about this other issue about how about the fact that actually the data is coming from lots of sources. So let's say that somebody wants to do predictive text. I don't know if you notice now, but when you do email, they kind of predict like the rest of your sentence. It's quite good. I think pretty soon, our kids, all they have to do is tab, and they don't actually have to structure sentences. But obviously, I don't want to give my text, or at least these companies don't even want to shepherd they don't want to take my text. That's the claim, at least. Let's say Google, because they don't want to be liable later that things will be found out about me. So they have been proposing in a sequence of paper how to not really look at people's data and still be able to use it for coming up with training data. And the first idea there, I think, was that you will compute a local model and then send it to them, like local weights for your prediction model, and then they will take all these local updates for the neural net and figure out a model. Then they realized that actually that's not good enough because a model itself can be reverse engineered. And the next idea there was to do a multi-party computation, really, so that these devices will do, in a sense, a multi-party computation with each other, the result of which would be a model, and send it to Google, say. So to me, it seems a bit unbelievable because multi-party computation is pretty expensive. This is their claim.
So now they're talking to each other, so that could be leaking now.
No. So multi-party computation, I didn't talk about it, but the whole point is that you can prove that talking to each other doesn't give anything except for the result. So this is using as a black box one of these cryptographic tools that have been developed in the 80s, 90s. This actually we can solve. But the communication is quite intense. So it could be that what they're doing is that there's some servers, Google servers, people they take their model, they might split it, into shares, and then these servers are doing a protocol that then reports to Google the centralized model. But then there's this question of who says that these servers actually are trusted is unclear. But that's what they argue. This is 2017. The last thing is, what about if people just steal your model? Okay, so forget about the training data and the private data. You already figured out a model, now they steal it. So there's a lot of evidence to the fact that actually just from the model, you could, it's kind of miraculous that you can sort of find training data. You can go back. There's actually, they show this in a sequence of papers. So what do? If you protected your data in the training time, and then a model was developed, and then anyway, just from using it, you can reconstruct it. So there is essentially a differential privacy comes into the rescue here. Almost, because in differential privacy, in the domain of learning, you could say, let's look at two set of training data. One of them, my data is in, one of them, my data is out, and somehow I'm going to do a differentially private learning algorithm. That means the definition is that you cannot tell those models apart, whether my data was in or out. The problem with that is that there's a huge gap in the sample complexity. You can do that, but you need a lot more training data to get the same results, a lot more, sort of prohibitively so. So then really, again, MPC here can sort of get the same gap complexity. Anyway, this is already too detailed. But are we done yet? I'm almost done. But I just want to say that all this was just about privacy. I think that trusting the users to give their data, trusting the servers to follow the protocol on the data they're given, is a lot of trust. And the trust but check, which this is Ronit's, I think, Gorbachev's picture. I think it's a fundamental question, and the stakes are really too high to pretend it doesn't matter, everything's going to be fine. Maybe it will be, maybe it won't be, but I think that it's ridiculous to assume it will be. And that's it. I think I'm done. Thank you.
Any questions? Okay, so
Okay, great.
wait for that.
Yeah.
So actually, it's going back to the beginning of your talk when you gave this nice like theory and practice going so well in cryptography, went very well in machine learning until this new age of prediction.
Yeah.
I'm wondering, is there anything you think the theory side should be doing to bridge that?
The one on the machine learning side. I think they are doing. I think it is being done, right? There's a lot of theorists now who are interested in giving guarantees for machine learning. I think it's already the case that even the community, the practice community, they do talk about definitions. I mean, they do talk about goals. Then in practice, you know, the point is that the neural nets are very successful. They might not be able to achieve the goals, but they're aware of them. So I think that it's a question of time. So this summer, like in Simons, we're going to have this theory of deep neural nets that Alexandre Madrazo and Samuel Benji are doing in 3 months, trying to, I mean, these are smart people, right? I believe that theory really it will get there. Maybe you have to modify the algorithms to some extent, but it's really a belief that is not based on my knowledge because I'm not a machine learning person. It's just based on history. Okay, yeah?
Just a comment. So actually, the Israeli healthcare system has been practicing fairness algorithms, and it works amazing. And if anybody wants to work on medical data, we have tons of it. And you're welcome to practice all your cryptography.
So when you say fairness, what kind of fairness?
Guy Rothblum and Homer Reingold,
Yeah?
the multi-calibration for the masses paper, amazing results.
Yeah, so this is a very interesting paper by a guy in Omer who also come from a sort of cryptographic education, at least, where they came up with a way to, after you have a learning algorithm that doesn't take fairness into account, how to kind of modify it so to not degrade in terms of its accuracy and predictability, but also achieve sort of parity for groups which are defined very generally, right? So it's not like you're targeting, I don't know, women or something that you want it to be as fair as men, but the definition is a general definition, right? It's recognizable sets, and they give an algorithm, and you're saying that it's used, so it's very interesting.
Adversarial machine learning for debiasing, stuff like that should work as well.
Okay, great. Thanks.
Okay, so let's thank Shafi again.